Welcome to the era of the megafab, where a worldwide renaissance in chip making is revolutionizing the technology landscape. This is where cutting-edge technology and safety converge, enabling the production of smaller, faster, and more powerful chips while prioritizing the safety of equipment and processes. Designers of wafer processing equipment are increasingly turning to performance-based functional safety standards. Unlike prescriptive standards that offer specific design criteria, functional safety standards prioritize desired performance outcomes instead of specifying precise methods for achieving them. This approach ensures reliable safety functions, even in the presence of equipment failures or dangerous faults. Machinery designers have faced a challenging and arduous learning curve while navigating through the constantly expanding landscape of international safety standards. Mark Fessler is intimately familiar with this journey, with over 25 years of experience as a member of the SEMI Standards Committee and more recently as the co-chair of the Risk Assessment Task Force. He serves as the Global Director for Product Safety Engineering for ASM, a manufacturer of wafer processing equipment.
You know, back in the mid to late 80s, there was no industry consensus standard for designing capital equipment that makes wafer processing tools. And there were some foresightful individuals who thought that a performance standard was needed. And they spent basically the end of the 80s, at least 3 or 4 years, getting input from the major customers in the US at the time, the major big players, which were IBM, Intel, Texas Instruments, and looking at what their internal specs were and trying to mold and build an industry performance standard for how to safely design and test and use wafer processing tools.
There are two key umbrella standards which semiconductor equipment manufacturers must follow: SEMI S2 and the European Machinery Directive. On January 1, 2012, the European Union adopted ISO 13849 as the harmonized European standard, replacing an older machinery safety standard called EN 954. ISO 13849 addresses the concept of interlocking as part of the overall safety strategy, or safeguards known to designers as safety interlocks. These interlocks involve a variety of sensors, switches, and controls, pneumatic, hydraulic, electrical, or software-enabled, that continuously monitor critical parameters, sequences, and process variables. If predetermined safety limits or conditions are exceeded, these safety interlocks automatically shut down equipment or isolate the process. ISO 13849 provides essential guidance and suggested methodologies to ensure the reliability of these safety functions, thereby reducing risks and eliminating dangerous undetected failures.
It is important to remember that most of the 13849 requirements were very heavily reliability based. Mean time to dangerous failure. How long is it going to be before this thing fails to danger, meaning it fails in a way that it's going to make something bad. That fail safe happens and you get downtime events from it. Fail to danger happens and you can get hurt. The interlock isn't doing what it's supposed to do. And nobody knows that. So you have fail to danger detected and fail to danger undetected. And the number one thing design engineers must care about is how often a fail to danger undetected occurs. That's the most important.
Well, any design engineer is going to be focused on the function of his or her design. That's going to be critical. They're going to be focused on making sure it works. But they also need to be realized they're responsible for how it fails. You need to make sure that's factored into your design, so your design is a fail-safe design. Standards are an excellent place to start from that, and good engineering also factors into it.
Safety interlocks are classified based on their performance level, or PL. A closely related functional safety standard, IEC 61508, introduces a similar concept known as Safety Integrity Level, or SIL. Both PL and SIL serve as quantitative measures of reliability, requiring the calculation of the probability of dangerous failures. These concepts originated from IEC 61508, often referred to as the mother standard for electrical, electronic, and programmable electronic safety-related systems. This standard has significantly impacted various industries, leading to the development of specific functional safety standards for process plants, the machinery sector, nuclear power, and automotive and rail transport. IEC 61508 has also provided valuable guidance to manufacturers of sensors, switches, programmable logic controllers, and other controls used in the design of safety interlocks. A notable case study is United Electric Controls and its Precision Sensors division. They collaborated with a safety certification organization called Exida to assess the performance of their StaySet pressure monitoring sensor used in a chemical deposition chamber. This evaluation involved a failure modes, effects, and diagnostic analysis, which systematically calculates failure rates, failure modes, and diagnostic capabilities at the subsystem or product level, essential factors in determining the performance level. Similarly, United Electric's 1 Series smart programmable pressure or temperature switch with logic underwent an FMEDA to certify its SIL capability. Exida, in addition to performing the necessary functional safety assessments, maintains a searchable database called the Safety Automation Equipment List. This resource provides convenient access to relevant documents and certifications related to functional safety. As semiconductor fabrication expands to meet the increasing global demand, the responsibility for designing and implementing safety functions is being shared by machinery designers and product safety engineers. This collaboration involves leveraging new performance-based standards, advanced tools and techniques, and an extended value chain of qualified suppliers. Consequently, semiconductor capacity is expanding while systematically reducing risks, thereby ensuring safer environments for personnel and the communities in which fabs operate.